Dickens. I'm the founder of Wildspark Technologies, and today I'm going to talk about our solution for compact propellerless vertical lift. So the heart of our technology is a microfabricated engine. So these are little engines that are made on the scale of microns. So you could fit many of these within the width of a single human hair. The way that they operate is they take the airflow over the engine and they ionize a very small part of the air flowing over it, turning it into positively and negatively charged air molecules, and then accelerating those molecules through an electric field. To the left, you can see a model of the air flowing over one of these devices and being accelerated very quickly to a high velocity. Because these are very small, you can make them in very dense arrays. You could pack thousands of them within a square centimeter. And by making them on flexible electronics, we can make them into arrays that you could wrap over very complex shapes. So here I've shown them wrapped over a sphere, but you could use them to wrap it over a drone or over existing surfaces like control surfaces on existing aircraft, on the bodies of existing aircraft, or even on things that you don't typically think of as wanting to have propulsion, like an airdrop package where you want to maybe induce just a little bit of torque to make sure that that package lands on the ground in the way that you want it to. So this project supports the Army modernization goals for future vertical lift. It opens up some new applications for UAVs. These engines are capable of responding potentially down in the nanosecond range. And so you add a capability that you can match with the fast decision-making capability of AI and machine learning. It opens up novel forms of thrust vectoring. You can orient these engines in different directions, so you can generate a force vector in any direction that you need. And again, they can be deployed over very complex shapes and airframes. This is an ideal form of propulsion and maneuvering for dense environments, so caves, forests, dense urban environments. And because it eliminates propellers from small UAVs, it eliminates the risk of having a propeller contact with personnel. So for things that are human proximate, like hand-launched UAVs, close reconnaissance, close resupply, is a very early stage and potentially disruptive technology. One commercial application that I want to talk about is the emerging air taxi and personal air mobility market. Several companies are looking into this, and NASA has invested in it very heavily. A concept where in congested urban environments, you would have a fleet of small air taxis that would operate from very small landing and takeoff zones, and able to move people around a congested environment, many of them electrically powered. So we feel that this technology can add to the capabilities of those systems. One concept might be to use this as a primary propulsion for vehicles like that, using a lifting body concept, where our engines induce airflow over a body, and then that generates lift, and then eliminates the needs for propellers, as well as all the clearances and safety issues created by having propellers in close proximity to people. And we could also use it as an additional capability to more mature technologies by adding fine maneuvering capabilities. So if you're trying to land a personal air vehicle in a very small space, you could get more maneuvering capability than you might be able to get with a traditional collective control from a rotorcraft. And also can augment existing systems by controlling airflow over wings and control surfaces. For example, in some concepts where an aircraft may take off vertically and then transfer to horizontal flight, either by rotating a propeller or even rotating a whole wing assembly, to help control the airflow and lift characteristics during that transition. So where are we today? So with the support that we got through the xTechSearch program, we were able to go into manufacturing, and we've built semiconductor die that we believe demonstrate all the principal components that we're trying to illustrate, and you can pass that around. So we've been able to detect electrically as well as physically that we're inducing airflow over these die, and we probably have one or two iterations of this needed before we can actually put together a UAV that's lifted and propelled by these die. But in the space that we've had, I think that we've answered a lot of the basic physical questions about what we need to do to make these engines operate. So that's a rigid substrate that those are fabricated on. We've worked with the NextFlex effort, which is working closely with ARL and DoD on other products. And we understand from a discussion that we've had with them what we need to do to be able to make our product compatible with their flexible hybrid electronics manufacturing process. And so the next revision of this product, we will be able to put it onto a flexible substrate, 3D print all the connections that we need from them, embed some of the support electronics for it, and then have that flexible membrane that could be wrapped over complex shapes. We've also taken the intellectual property that we've generated in this time since the xTechSearch began, and capture that in a patent application. I want to talk a little bit about how we developed these engines. So we were actually in the clean room before the money hit our bank. We have done several different revisions of building these engines. So we can roughly divide that into a couple of phases. So our first test product we called Tiger. We used it to validate some of the manufacturing processes, to look for different material systems that would work with what we're trying to do. We put on several different designs as well as test structures, and then built those and tested them, and then took that data and used that data to build better simulation models that we could use to generate our next iteration, which we call Alpaca. And on this, we have an additional 9 designs and some additional test structures. All of these die are electrically functional, and several of them we've observed airflow over. While we've observed that these seem to be working, they seem to validate all the basic physical principles, what we've learned from this round is that the airflow that we're generating over the devices seems to have some turbulence. It seems to maybe not be completely directed the way that we need it to be directed to generate useful thrust. So in our next revision of the process, we're going to take the lessons that we learned from this and resolve those issues to get us to a higher level of thrust that we can use to put these on UAVs and demonstrate them in a real system. And so some specific goals that we have from that are we want to be able to demonstrate that we can generate 1 gram of thrust per watt as a starting point with at least 5 grams of thrust per die and a power density of at least 1/4 of a watt per square millimeter of die surface. So I'm going to show a video here, but first it needs a little bit of explanation what it's going to be showing. So this is a die that's on an electrical test system, and I'm feeding test signals into it, and we're looking at it through a microscope. And I was looking for evidence that we could see things moving around. So to start off with, I used these polystyrene spheres that you can buy. They're used for calibrating different types of metrology equipment. They're kind of heavy, and unfortunately, they also kind of stick to the materials that we're using. But in several tests, we were able to observe them move around, so we'll see that. Then after that, I just looked for other substances that we had that might show the movement a little bit more clearly than these heavy polystyrene balls. So in the second clip, you'll see some just baking soda scattered over a wafer. And what you'll see there is the baking soda particles will kind of pop up and move around the die, but they'll move around mostly in the direction that we want movement to be, which is from top to bottom in this video. But you also see some kind of chaotic and circular motion as well. The third video shows just a piece of cotton that's been suspended over the device. And so you'll see, as we ramp up the power, you'll see it very slowly move away from the device. And then at the very end of the video, when we cut power, you'll see it spring back to its original position. So these are the heavy polystyrene balls. And so that was kind of typical. We see them move, and then they kind of stick, and then they move again, and then they kind of stick. So kind of intermittent motion like that. This is the baking soda. You'll see it hop around randomly over the die surface, mostly moving from top to bottom, but some of it moving, in little vortexes. And then finally, here's the cotton, and so you'll see it slowly begin to move downward, and then at the very end of the video, when the power is cut, you'll see it spring back. So where do we go from here? So to develop our next generation part, we really need to understand what's going on with our current part. So we're looking to additional partners to find ways to understand what's going on with the airflow over this device. There's a technique called particle image velocimetry, which is basically what we were trying to do with the baking soda and the little polystyrene balls. But there are techniques that can be used for very small systems like this in an air, and we need to learn how to use that properly and find somebody who has a world-class setup that could let us detect sensitive flows. Thermal and UV imaging, we think, will help us. We're putting a lot of power in these devices in some cases, and we want to know where that power is going, how much of it is going to heat, and how much of it is going to motion. Thermal imaging will help us determine that. UV imaging will help us understand where the actual ions in the plume are going. And optical spectroscopy is a technique where we can actually look at the device and try to understand exactly what ions are being generated in what proportions. So our general process has been to use the physical data that we get off of real dye and then update our simulation models and then use our simulation models to help guide us where we need to design our next series of devices. We've discovered some meaningful differences in the electrical characteristics that we're seeing on the real dye versus what we have in previous simulations. Part of that is due to the influence of the other things that we need to put on the wafer in order to get these to work. Routing the wires, putting in bond pads. So we need to update our simulations to include all of those different effects. And as I mentioned earlier, the airflow seems kind of chaotic. It's generally moving in the direction that we want, but when we look at particles, we see some particles moving in directions that we don't expect. So we need to understand what's going on there from an aerodynamic perspective and see what we can do to channel that airflow so that we get the most thrust out of these devices that we can. So some of that is going back and looking at the characteristics of that airflow over the materials that we're using. We use an unusual set of materials, and so we may have to look at additional coatings to make them aerodynamically smooth. We may need to look at things like 3D printing nozzles in order to get the airflow to do what we want it to. Some of the key learnings that we have from going through this process, we tried several different material systems. We used some unique materials in making this device. And we had a lot of success in by picking the right materials and getting the performance characteristics that we want. So just as a figure of merit, when we started this, the turn-on voltage, which is the voltage that we apply and we first begin to see ions move across the device, was about 160 volts. And by changing materials and geometries, we've been able to reduce that to below 20 volts. Right. Yeah, so there is secret sauce. There's a lot of secret sauce. So, and actually, let me expand on that point just a little bit. So if you're familiar with plasma physics, there's an empirical law called Paschen's law, which generally describes, if you have two electrodes and you want to strike a plasma between them, how much voltage do you need to strike that plasma? And an interesting thing about it is that as those electrodes get closer together, you go through kind of a minimum, and then the amount of voltage that you need to strike a plasma actually goes up as you get things closer together. And the reason for that is that what typically happens in a discharge between electrodes is you have a chain reaction that happens in the medium between them, right? So you have some charged particles and you accelerate them, and they collide into each other. As they collide, they generate more charged particles, and then you have a chain reaction, and you need a certain distance to allow that reaction to happen. If you get too close, then you actually damp that because you just don't have enough time for those particles to hit each other. And there is some secret sauce that allows you to operate in a regime that is much tighter and much smaller than what Paschen's law would suggest. And the advantage of doing that is that instead of having to use something in the high kilovolt range, you can use something that's in a much more reasonable voltage range. That's DC. So, I guess to talk about somebody else in the field, right, there's a paper that was published a few months ago by a group at MIT where, they're using kind of a large scale ion propulsion system that their technology is very different than what we're proposing, but they used a 40,000 volt power supply versus, our devices will run as low as 20 perhaps. So Other progress that we made was in the power handling and stress capabilities of these devices. So we've been able to demonstrate power densities on the order of 0.5 watt per square millimeter, and been able to maintain devices at those power levels for perhaps 10 minutes or so without any indication of problems. We've also been able to demonstrate that we've been able to put 400 volts across many of these devices. Again, for probably around 30 minutes or so without seeing any degradation due to that. So where that's important and where that interfaces with that turn-on voltage that I was just talking about is that turn-on voltage, you can visualize it as when we first start turning on the tap. And then that maximum voltage that we can withstand is how hard we can push after we begin turning on that tap. So the combination of being able to turn on that tap very early and then being able to push very hard after that is what will get us to the point where we can move enough air to generate usable thrust. One of the key worries about building a system like this is because we're generating ions, and those ions are going to impact the device itself. They're going to be accelerated by electric fields into the device itself. Worried about how long it's going to take for the device to wear down in air. And through choosing some clever materials, we've been able to demonstrate that these devices can operate in air. So far, we've run them up to about 30 minutes without seeing any degradation. And there's actually kind of a funny story behind that also. So, in the fab, I've been trying many different material combinations. And so one of the material combinations that's on that wafer that I just handed around, I put down the material and then I patterned it. And then to form a pattern on the wafer, you use a plasma etching process. So I took the wafer, after putting that material down, I put it into a plasma etcher. I ran a very aggressive plasma etch on it. It came out of the plasma etcher and it had been untouched. So it's something much more aggressive than the device operation, putting it into a machine tool that's supposed to specifically etch it with a plasma. Had to go back, use a different tool, use a much more aggressive recipe in order to even build the device. So that gives us some confidence that operating in air where we're generating ions and slamming them into the device, that will have a good lifetime. I wanted to talk just a little bit more about how we use the physical data that we get off of the device. So on the left there, that's an actual voltage current response from the device. So we're sending in a test voltage and measuring the amount of current that that device is consuming. And then on the right there, you see some of our simulation models. We're modeling things like the concentrations of electrons, concentrations of ions, and we can calculate what we expect those current voltage characteristics to look like. And by comparing the differences between them, we can fine-tune our simulation models, and then that helps point us in the direction of how to optimize the device. This is the demonstrator proof of concept that we're working towards. So what we want to do is take a tennis ball-sized drone, coat it with a flexible membrane of these die, and then be able to demonstrate that we can lift and hold a target weight of 55 grams and be able to vector the thrust and demonstrate axis control. This is our overall roadmap, just showing where we've been and where we see ourselves going. So we're doing a lot of work in parallel right now with the control electronics to be able to control a drone. And as I said before, we anticipate one more or perhaps two more iterations on the die itself to be able to get to lift that target weight. So I want to give a bunch of thank yous here, but most importantly, I want to thank ARL and the xTechSearch program for letting us go forward with this work. At the time that we originally pitched this, this was an idea on paper. It was backed up by some simulations, but we hadn't had a chance to go into a fab and actually build stuff. Being able to get through 2 rounds of building stuff in the fab and have something that's wiggling its fingers and toes is a huge step forward for us. I also want to give a shout out to the technical team. So myself, my background is electrical engineering. I have about 20 years in semiconductor device fabrication experience, the microelectrical mechanical systems, CMOS devices, and RF electronics. Also working with me to do the fabrication is Jim Baird. He also has about 27 years of semiconductor fabrication experience. And Professor Raja from the University of Texas Aerospace Engineering Department is working with us to fine-tune the simulations and bring some of his knowledge of aeronautics and plasma physics to the team. Finally, I want to thank the places where we did fabrication. So we used both the Cornell Nanofabrication Facility up in Ithaca, New York, as well as the Texas Nanofabrication Facility in Austin, Texas. And down there on the left is a little selfie of us in the clean room building some devices. So thank you very much for your time, and I'd like to open up the rest of the time for questions.
So for the chip that you manufactured or the fab that you've done, are each of these engines individually addressable, or is it in as an array, or how are you controlling the I guess the firing of each of these engines?
Yeah, so the vision is that they'd be like pixels on a screen. So they'd be individually addressable. Now the engines themselves are so small that each pixel would actually have several different elements in it. So you might actually have like 100 elements within a pixel. But the size of that pixel would still be very small, maybe 0.5 millimeter by 0.5 millimeter or 1 millimeter by 1 millimeter. Those test structures that you're looking at, those are all 3 millimeters by 3 millimeters. And they're only addressable in those 3 millimeter by 3 millimeter blocks.
And do you know what ions you're generating? I mean, is ozone one of the ions that's being created?
So we're primarily generating O4 plus, and
Okay.
the decay path from O4 plus does not go through ozone. There is some ozone generated as part of the process. We would expect that there would be. We also expect that there's probably some NO type compounds generated. In simulations, it looks like we can do some things to control the development of those byproducts. They are going to be present. And so going forward with the technology, understanding what that impact is in generating ozone and NO compounds is going to be important.
Okay.
So you mentioned you're observing some turbulent flow over it. Do you have a sense of, I assume you have predictions on what sort of induced flow you wanted to see and kind of where you were actually at? Do you, in terms of just predictions of what sort of induced ion flows, ideally, were you out of I guess you called it a pixel,
Right.
a 10 micron by 10 micron pixel, like?
So off of these test devices, I was expecting to see flow rates on the order of about 10 meters per second for the ambient air flowing over them. The one thing that may be impeding that is that the topography on these wafers, where we bring in the supply currents, we've got some significant step heights, and so that may be interfering with the flow of the air over the device. The other thing that we need to more seriously consider is that we have the device itself, but then we also have the electric fields from the wires that are bringing the signals in. And that is having an effect on the flow field as well.
So you mentioned there could be hundreds of these things on a pixel. Is the turbulence like at the connections between them, or is that the turbulence is occurring just over one clean little jet?
Yeah, so I think to really answer that, we really need some better analytical techniques. But what I seem to be seeing right now are two things. One is at the edge of the device, there seems to be, you'll sometimes see particles kind of spin around or actually move counter to the direction that you expect. And I think that what we're seeing there is we may have flow over the device, but then that flow breaks up when it exits the device. So we need to control that regime a little bit better. Maybe by contouring that surface or selecting materials where that airflow can stay attached longer and controlling that exit from the surface and where it goes into the next device. The other thing that I've seen is that on the edges of the device, we seem to see some counter movement. And I don't understand that. I don't know if that's due to the electrostatic effects of the boundary of the device or the wires coming into the device, or if we're actually seeing little vortexes that we're generating around the edge of the flow. It's probably going to be a combination of both. Any other questions?
I have one.
Yes.
So you had shown the tennis balls that you're saying that your next phase would to be able to move a something to that size.
That's right. Yeah, so where we are right now is the die that I just passed around is compelling evidence that we're seeing the basic physical principles are working. But we need one or two more rounds of learning to get something that's going to give us enough thrust that we can put on to a tennis ball like that. So in the next revision, we're going to aim to solve some of the airflow issues that we're seeing and crank up the amount of thrust that we can get out of it. The other thing that we're going to do in the next revision is that working with NextFlex, we understand what we need to do from a device perspective to make our devices compatible with their flexible hybrid electronics manufacturing process. So it'll be our first time trialing that with devices that can be used in their processing. Thank you for your time.